Hi everyone, this is Manu, and if you came to the review this afternoon, you may have noticed that we didn't really get through a lot of the cache problems that were on the review, but we felt that since caches are such an important topic and that they tend to show up on all midterms, that it's really important to get some good practice in with caches. So I'm going to go through the cache problems a bit more in depth from the review, and hopefully you guys following along can get a better sense of how to approach these types of problems. So I'm going to start with the very first cache problem, which on the review is on slide 50. So let's get started. So here, the first thing to notice with every cache problem is the parameters that we set you up with. So if I'm going to write them down, we have a cache size of 256 bytes and direct mapped block size of 4 bytes, and our write policy is write allocate write back. So what does all of this stuff mean, and what can we sort of glean from this information? Well, the first thing I like to do is to convert all of our numbers into powers of 2, because generally with cache problems, we're often dealing with powers of 2, and there's a lot of division and multiplication, and you'll see as we do the problem how life becomes a lot easier if you just deal with everything in terms of powers of 2. So usually I'll just start by converting this into 2 to the 8 bytes, and this into 2 to the 2 bytes. Alright, so what does all of this stuff mean? Well, first let's try to sort of maybe draw the cache and visualize what it looks like. So remember, all caches are just tables. They're just a 2D table. And they all have blocks and rows. So going down, we have our index. And these are the rows of our cache. So they'll be numbered, 0, 1, 2. And first we have to figure out how far down do we go. So how do we do that? This is calculating the number of rows in our cache. So how do we find the number of rows? That's simply the size of the cache divided by the block size. So that's powers of 2 coming in handy here. 2 to the 8 divided by 2 to the 2 gives us 2 to the 6 rows in our cache. And so that means our index is going to go down to 63. That will be our last index, which is 2 to the 6 minus 1. And what's here? Well, we have a direct map cache. This is where this factoid is important. It's direct map, so that means each index is associated with exactly one cache block. So over here I'm going to write offset, and we'll have, byte 1, byte 2, byte 3, and byte 4. Cool. So basically, we can visualize our entire cache as a 2D table where each row stores exactly 4 bytes. And the offset is within 1 block. This is just what our cache looks like based on these parameters. So what else can we glean? So the next very important thing when we do any cache problem is to figure out the tag index offset breakdown. So I've kind of done this already, but it's important to write down how many bits are in each thing. So we've got the tag, we've got the index, and we've got the offset. So the offset we can just determine directly from our block size. So a 4-byte offset, again, powers of 2 coming in handy here, we just read off the power exponent there and get that the offset is 2 bits. How about index? Well, we found the number of rows is 2 to the 6 rows, and since our cache is direct mapped, that means there's 1 block for every row in our cache, which means the index bits is just exactly this exponent. So why is it not always just this number of rows? That changes when you get a set associative cache in which you have multiple blocks per rows. So maybe let's say we had a block size of 4, a cache size of 256, and it was 4-way set associative, then basically we would have to divide the number of rows by 4, or 2 to the 2, and get that we have 2 to the 4 index locations, which is 4 bits for our index. And so finally, our tag. So in this problem, we actually don't tell you what our address width is, so you can't determine how many bits are in the tag, but it turns out that this doesn't really matter for this problem. But when would you be able to figure this out? Is if we gave you the address width. So let's say if it was 16-bit addresses, 16-bit addresses, that would mean our tag is, let's see, 16 minus 6 minus 2, that's 8 bits. So it'll vary depending on how many bits your total address takes up. Great. So now we figured out our tag index offset breakdown. We figured out what our cache looks like. What's the last thing we have to think about here is our write policy. So we're telling you guys that it's a write allocate, write back. I forgot the word back. So what does that mean? So in the review slides, we actually cover more in depth what these policies mean, but briefly, write allocate, write back means that whenever you do a write to memory, then write allocate means you pull the data from memory into the cache, and write back means that instead of writing only all the way back to memory every single time, we'll just keep the data in the cache, and we'll write it in the cache, and only write it back to memory when we do a cache eviction. So that's important to know when you're doing these cache problems, is how do you deal with writes? And this is what your write policy tells you. Okay, so now I think we understand exactly how this cache looks, and we can try running it on some of this code. So let's start by just writing down the relevant pieces of code. Again, this is slide 50 on the review slides, and see what we can understand from the code. So the way this problem is set up is we give you this array, and we give you 4 for loops. And the first part of the problem is just running for loop 1. So that looks like this. All right, so what is happening here? What can we figure out? All right, first of all is to notice that we have a char array. And so in this class, for the purpose of this class, a char is always going to be 1 byte. And our array has 512 characters, so our array is 512 bytes. What else is important? Well, we don't tell you this here, but generally you can assume, and on a real test we'll make this clear, is what the actual address of the array is. And so for when we're thinking about where to put our data in the cache, we'll tell you where the array starts at in memory. So for now, I'm just going to assume that the address of A is 0. So that means our array starts at memory address 0 and ends at memory address 512. Great. And now we'll look at what our loop is doing. So it's a pretty simple loop. We're stepping by 1. We're going 1 character forward each iteration, and inside we're just storing the value 1 inside each slot. So we're doing a write to each spot of the array and storing the value 1. So now we have to figure out we have to calculate 2 things according to the problem. We have to find the hit rate, and then we also have to find what types of misses are happening. Cool. So let's go through a few examples. Usually the way these cache problems work is you'll try them on a few addresses, you'll find a pattern, and then be able to generalize that pattern to the entire loop. We're not going to make you go through 512 loop iterations and figure out some crazy hit rate. So let's just try a few examples and see how that works out. Okay, so let's start with our first address, so I equals 0. What's going to happen here? Well, first we want to find the tag index offset. Let's just ignore the tag. It's going to be some size, but let's find that. So the offset here is 0, the index is also 0, and the tag is, well, it's going to be 0 because the remaining bits are 0. So the way I figure this out is if you just turn this 0 into a binary representation, maybe take the first 2 bits, it's going to be 0. The index is also 0, and the tag is 0 because I is just all zeros, right? Okay, so we're trying to access I equals 0 in our first loop iteration, right? So, well, our cache is empty, so it's going to be a cache miss. But what are we actually going to be doing? Well, we saw that it's a cache miss, so we pull address 0 into the cache. And when we pull something into the cache, we pull all the blocks of data, or we pull the entire block of data into the cache. That means this is going to contain 0, this is going to contain 1, and all the way up to 3. So these are the addresses. I'm writing the addresses that are stored in the cache. Okay, so, well, we said that it was a miss, but what type of a miss? This is a compulsory miss. And how do we know that? Well, a compulsory miss is whenever there's a miss in the cache, and it's due to the fact that we've never actually asked for this address in our sequence of accesses before. So this is the very first loop iteration. We've never asked for address 0, which means it's a compulsory miss. Okay, so we've got one compulsory miss for our first address. Let's look at the next one. I equals 1. Same deal. Offset is 1. Index is still 0. Tag is still 0. Okay, well, great. We actually already have this in our cache because we pulled in the entire block the very first time. So this is going to be a hit. About I equals 2. Very similar. Do the tag index offset, and it's a hit because it's right here. And then I equals 3. Same deal. And it's going to be right here. So we have 3 hits after the miss. Let's go to the next iteration. So we got I equals 4. What's different here? Well, our offset's 0, but now our index goes up 1 to 1. And if you want to verify this, again, you can just split this 4 up into binary, and the first 2 bits will be 0. The next 6 bits will give you the number 1 for our index, and the tag is still 0. Great, so where does this go? Well, we look inside index 1, and we're like, oh, this is empty, so we're going to have a miss. But we're going to pull in the entire block. So we'll get 4, 5, 6, and 7 in our cache. And again, this is going to be a compulsory miss, because we've never seen this before. All right, and how about the next? I'm going to go a bit faster here and note that I's 5 through 7, well, the offsets are going to be 1 through 3. The indexes are all 1. The tags are all 0, but we've pulled this whole thing into our cache. So this is 3 hits. And maybe now we're starting to see a pattern here, because every for loop iteration, it looks like we pull in a new block, and then the first iteration is a miss, and the next 3 are hits. So it's going to happen here, here, and it's going to happen for the next iteration and the next one, and really all of them. So we can kind of see a pattern here, and it's clear that we have the same one for every group of 4 iterations. So we can actually, rather than going through all 512 loop iterations, we can kind of cut it off now and generalize and say, okay, so I get 1 miss, 3 hits for every 4 iterations. What does this mean for our hit rate? Well, if it's every 4 iterations, 512 evenly divides 4, so we're going to have an equal number of chunks, and each chunk is going to have a 75% hit rate, which means we end up with a 75% hit rate. And what about our misses? Well, since we're pulling in a new address, we're only accessing each address once in this loop, then we're going to have every miss be a compulsory miss, because we've never seen any of these addresses before. So we have all compulsory misses. Great. And now, the last thing to figure out is, what does the cache look like at the very end of this problem? Because there's 4 parts here, and each loop runs one after the other without clearing the cache. That's important to know, that the cache is not cleared at the end of each loop iteration. So when we're doing our second loop iteration, we'll have to think about what data has been in the cache after loop 1 ran. So let's just sort of go down the line here. So 2 is going to be filled in, addresses 8 through 11, all the way down to what's going to be filled in at this bottom row. Well, we're going 4 addresses at a time. So by the time we hit index 63, we'll be at the end of the first half of the array. And you can see this because our cache size is 256 bytes, and our array size is 512. So our cache can basically fit exactly half of the array. And so the bottom here, we're going to start with it being 252, and 255. Great, but that's only half of our loop iteration. Now we have to go the second half of our loop. Well, that's addresses 256 up to 512. And so what's going to happen, let's just look at I equals 256. All right, our offset is 0. Our index, what's our index? Well, 256 in binary has a 1 all the way in index 8, which is actually past our index and offset. So our index is going to be 0, and our tag is going to be 1. And what does that mean? Well, our direct map cache will go to row 0 and be like, oh, the tag here is 0, but you want tag 1, which means we'll have to kick out the data here, evict it, and according to our write back policy, we're going to have to write this back to memory, and then we're going to have to pull in our new cache line. So this is going to be replaced with 256, 257, 258, 259. Great. And then this is actually going to happen for all the rest of our data. So 260, 261, 262, 263. And note that this is still the same pattern. 1 miss, 3 hits, even in the second half of the array, because it's all new blocks. And so finally, at the end here, I'm just going to erase these because I don't have enough space to write both. At the end here will be 63 is the last 4 items in our array, which is 508, 509, 510, and 511. So this is what our cache is going to look like at the end of our iteration, is it just contains in order contiguously the last half of the array. That doesn't affect our answer for part 1, but it will affect our answer for later parts of this problem. And that's what we're going to do now, is part 2. Okay, so I'm going to redraw this cache with the state that we ended up with. 1, 2, 3, 4, 5. And then this one isn't there anymore. Okay. And then we have the same numbering. And now we have, let's just write in our data. So I'm going to write, rather than writing all 4 numbers, I'm just going to write the starting number of the index. This is what our cache looks like now. So now let's do part 2, okay? So we've got the same character array, but we have a slightly different loop. So we're saying for I equals 0, again going all the way to the end, but now we are jumping by 2. So what does that mean? Let's look at some addresses again. So what are we iterating? We're saying I equals 0, we're doing I equals 2, 4, all the way up to, we're doing 250, I guess I'll write, 256, and we're all the way up to 510, right? And this is the same breakdown. This is going to have the same tag index offset as this one in the previous problem, but let's look at what actually happens when we run this sequence of accesses. Okay, so first we start with I equals 0, but oh no, it maps to the same part as it did in the previous problem, but now we have a different tag. We have our tag 1, which was left over from the previous problem, which means we don't have the data we wanted in the cache. We have to kick it out. Remember, because this is direct map, so we can only store 1 block per index. So I'm just going to cross this out and write the new address that we have stored. And now, so that counts as a miss. And what kind of miss is this? So this is not a compulsory miss. Not compulsory because we've asked for this before. But now we have to figure out, is it a conflict miss or a capacity miss? So here's what we do when we want to think about what type of miss it is. So if we figured out that it's not a compulsory miss because we haven't asked for this address before, now we want to think about, would this still be a cache miss if my cache was fully associative? And so now we can talk a little bit about what a fully associative cache would do in this situation. So let's pretend we had a fully associative cache for part 1. And what fully associative means is that essentially all of the blocks are in the same index. There's no, you don't map to some row in the table and then go to find a block. All the blocks are in the same row. Let me just draw this really quick. So fully associative. Actually, why don't we write the tag index offset breakdown for a fully associative cache? So in a fully associative cache, all we're saying is that we essentially don't have an index because it's always index 0. So that's just actually absorbed into the tag, and then our offset is still 2 because the block is still 2. So now how does this work? Essentially a fully associative cache works by saying, oh, is this block anywhere in the cache? No? Then let me put it in any of the empty slots using some replacement policy, but it'll put it in some empty slot in the fully associative cache. So back to this problem, we're asking, oh, I got a bit ahead of myself, actually. No wait, never mind. Okay, I equals 0. So yeah, so if this, let's say we ran part 1 with a fully associative cache. So we are just putting each new block in any available spot. Well, is this going to change what our cache looks like at the end of this problem? Actually, it's not, because we're pulling in all the blocks in the array, and we're pulling them in order. So the way it's still going to run through and fill in all the blocks with the first half, then all the blocks with the second half. So at the end of the day, our cache will still look essentially the exact same. It'll have all the blocks will be filled with the latter half of the array, which means that I equals 0, if we had a fully associative cache, we would still get a cache miss. That means it's a capacity miss, because the only way to have made this not a cache miss is to have made literally just make the cache bigger. If the cache were like 512 bytes, then we could have actually stored the entire thing in the array, and then we would still have our old data back in where we wanted it. So I'm going to call this a capacity miss. Let's look at I equals 2. Well, it's got the same index offset breakdown as from the previous, which is now still row 0, and we have a hit because we've stored the entire block in our cache. So this is going to be a hit. And how about I equals 4? Well, we have the same problem as before, where 4 maps to index 1, but that's not what we have in our cache. So we're going to pull in the new data, and then this is going to be a miss, and for the same reason as before, it's a capacity miss. Okay, and then 5, I'm just going to write that one down. 6, that's going to be a hit for the same reason as 2, and then, well, we actually see a pattern here. We don't really need to, for the purposes of hit rate, go through all the entire I's here. We see a very similar pattern to what we saw in part 1, which is for every 1 miss, we get 1 hit. Why is this different? Well, in the previous part, we had each loop iteration covered 1 byte, but here we're skipping by 2, so we actually only get 2 loop iterations per block of the cache. So here we get 1 miss and 1 hit for every 2 iterations, and this implies a 50% hit rate. And what about our misses? Well, it's going to be the same thing. If you ran through the entire problem, you'd see that we keep having old data, because, if we go to 256, that's going to be the same index as here, and it's going to conflict with this 0 through 3 block, and that's, again, going to be a capacity miss, because our fully associative cache still wouldn't have saved us from getting a miss here. So all of our misses are going to be capacity misses. Okay, great. So that's the first 2 parts of the problem. Let's move on to part 3. Okay, so I'm going to redraw the cache again. Again, if you notice, we're running through the entire array here, so at the end of the day, we'll actually have the same state that we had at the end of problem 1, which is the last half of the array is filled into the cache. So yeah, maybe I could just write 252, and then I guess cross that again, and we get 508 again at the end. Okay, Great. So now we're on to part 3. And this is a slightly different for loop, but let's draw the cache again. 1, 2, 3, 4, 5. I'm going to draw some more rows here. Yeah. Okay. We'll do more if necessary. Okay. Oh no. There. Well, split this very. There we go. 8. Okay. Cool. So we'll see why this is useful in a moment. So why don't I write the for loop again? So this is another different for loop. Same content, but different stride. Here we're going by 32, and we'll see how that plays out. But again, first let's fill in the cache with the old state, which is the latter half of the array. So something like this, blah, 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 all the way up to 508. Oops. Well, why don't we just go with whatever this would be? Yeah, we'll get there. Anyways, okay, so, okay, let's do some, same thing, let's just do some problems and see what we can find. So I equals 0, and the next one was I equals 32, because we're skipping by 32, 64, and well, let's actually, before we go all the way, let's just think about how many accesses we're actually doing here. Well, there's 512 is 2 to the 9. 32 is 2 to the 5. So that implies 2 to the 4 accesses. So we're actually only doing 16 array accesses. Here we're doing 256, and here we're doing 512. And so it's we're actually accessing way fewer pieces of data, and we'll see why this is important soon enough. But again, we're going to the end of the array, so the last access is going to be 480. Yeah. Okay, so let's just go through this again. All right, I equals 0. Same story as before. We had the old data in the cache, but we want the we had the latter half of the array, and now we want the beginning half. So we're going to lose this again, and this is going to be, well, it's not a compulsory miss. Again, is it a conflict miss? Well, no, because we filled in the entire cache before, so making the associativity greater wouldn't really have helped us out. So this is going to be a capacity miss again. Now, how about I equals 32? Well, where is that going to be in our direct map cache? Let's do the tag index offset, or offset index tag. Well, offset 0. What's the index here? Well, it's essentially the 8th block in the cache, so it's going to be index 8. And then, how about the tag is going to be 0? Well, so we go down all the way to block 8, so we're kind of skipping 7 blocks in our cache, and we're never going to fill those in because we're skipping by 8 blocks every single time. You can already see that something's not good is going to happen. But cool, we go down to 8, and this is going to contain, again, the latter half of the array, so we're going to have to cross something out. So it's going to be a miss, though, and now we're going to put in 32 through 35, and that's going to be a miss, again, from capacity. Okay, how about 64? Well, that's going to skip down another 8, because we have offset 0, index 16, tag 0, and that's going to be another miss. Again, another capacity miss, because we're still in the first half of the array. So, going down, you can kind of see, well, let's go exactly to the midpoint. Let's do I equals 256, and you see that this is going to happen because 256 is a multiple of 32. They're all powers of 2, right? Offset 0. What is our index here? Well, this is the 2 to the 8 over, this is the 64th block in the cache, right? This is going to be at the bottom. So it's index 63, 64. Oops, wait, oops, it wraps around, that's the whole point. And then tag equals 0. Right, okay, great. Now, let's see what happens. Okay, so we go back, just as always when doing 256, we go back to the first row in the array, and we say, oh no, it's block 0 through 3. So this is going to be a miss, but what kind of miss is this? Well, it's not a compulsory miss because we've already asked for this before in previous loop iterations, but is it a conflict miss? Well, so let's say we had a fully associative cache. Let's just simulate how this would run if we had a fully associative. So let's backtrack to the end of part 2 where all of our blocks are the latter half of the array. Well, what if we now ran with a fully associative cache with some smart, you want to assume the best replacement strategy possible. So if our fully associative cache, we accessed, how many actual blocks did we pull in before getting to 256? This time it was only, well, we're skipping 2 to the 5 every time bytes, so that's going to be, we're pulling in only 8 blocks before. So this I'm just going to write 8 blocks, which means if we had a fully associative cache, we would have only kicked out 8 blocks before we got to I equals 256. So if we were smart and were able to replace 8 blocks that weren't I equals 256, then we actually would have still had our block from the previous scenario left over. So this actually could have been solved with a better, more associative cache. So we're going to label this a conflict miss. And then you can see that actually for all of the remaining 8, there's going to be 8 blocks here and 8 blocks here. You can see that the remaining 8 are also going to be all conflict misses, because again, if we hadn't kicked those blocks out in the beginning, which we assume that in a good replacement strategy you wouldn't do that, then all of these would have been hits with a more associative cache. So we have 8 blocks, and they're all conflict misses. Okay, so we can actually do our hit rate now. Well, we've noticed that the first 8 is all capacity misses, and then the last 8 are all conflict misses. So we have 100%, 0% hit rate, and we have half conflict and half capacity misses. Okay, so that's all there is to part 3. Now, before again we move to part 4, let's think about what our cache will look like. So forget about the fully associative thing. Let's go back to our direct mapped cache. So in our direct map, our 256 conflicted with our 0 through 3. We'll have 256 here, 8 down later, we'll have 290. Yeah, and no, never mind. We'll have 288. And then, so essentially we'll have the last half of the array, but like skipping 8 blocks, or skipping, every 8 blocks. And now let's do part 4. And unfortunately, I'll have to turn this over to a new page. Okay, so part 4 is actually the same loop as part 3, but let's just redraw the cache. And I'm going to abbreviate here by just skipping blocks. So we have 0, 8, 16, all the way down to block 56, right? Yeah. And then this one at the end contains 256, 288, all the way down to 480. Okay. So let's do our loop then. For I equals 0, I less than 512, same loop. Okay, let's do it. All right, I equals 0. Well, what do we have? Well, it's going to be the same tag index offset as it always was, and it's going to be a miss as it always is, and we're going to get this. So, what kind of a miss? Not compulsory, because Well, we've asked for this before, but is it a conflict miss? In fact, it is, because if we go back to our fully associative idea, remember, our cache can hold a total of 64 blocks, and these last two loops have only accessed 16 blocks. So if part 3 ran with a fully associative cache, it would have contained the entire 16 blocks that we needed for this last iteration, or this last loop, I mean. And so if we had a fully associative cache, we should have had all the blocks we need. So this is going to be a conflict miss, because it would have prevented this type of miss. And then how about I equals 16? Well, it's, oops, did I miss I equals 32, I mean. Same problem. We go to this guy and we say, oh no, we have to kick you out, but this problem would have been solved with a associative cache, because we're accessing the exact same set of blocks as in part 3, but because our cache is direct mapped and can only fit one block per index, we have to have this eviction situation. So as you may see, this will go all the way up for all of the blocks. They're all going to be misses, and they're all going to be conflict misses. So here we have, again, a 0% hit rate, and we have all conflict misses. Okay, and that's actually all of the parts for this problem. So generally, in summary, kind of the approach that we took to doing all of these problems is, at the very beginning, we looked at our parameters and we sort of drew the cache. We visualized what is this going to look like in a real computer, and how is it going to split up our data with the tag, the index, and the offset. And first we figured that out. Then we also noted the write policy, which is how is it going to handle our writes, which in this case was that you pull all the stuff into the cache and do the writes in the cache. And then really for all of these problems, we first sort of did a few examples. We started with a few iterations, we broke them down with tag, index, offset, and we figured out what's going to happen to our cache over a few iterations. And we kind of get a sense of, oh, there's this repeating pattern that's going to occur for all of our or all groups of loop iterations. And we can do a little bit of arithmetic and realize that if you have this pattern, this is going to be your hit rate, and for all of your misses, these are going to be the type of misses. And then the last thing we made sure to do, because this is a multi-part problem with a cache that's not cleared every time, we had to figure out, okay, what does the cache look like at the end of this problem? That way we can do the next problem properly. So that's generally how we did it. And then maybe before we wrap this up, it's just I like to summarize generally how I like to think about what types of misses, because we asked you guys to categorize what type of miss each was. And so here's a convenient step-by-step process that you might use to determine what type of miss you have. So it's a pretty simple 3-step process. So if you have a miss, which means you already determined that this is going to be a cache miss. So has this address been asked for before? If the answer is yes, then that implies a compulsory miss. If the answer is no, go to step 2. Step 2, now we have to figure out, is it a conflict miss or is it a capacity miss? So we asked the question about the fully associative cache. If we had a fully associative cache with the best possible replacement policy, so this is the ideal case where we replace really the best blocks that we could choose, not some worst case scenario. So with the best case replacement policy, would this be a miss? So if the answer is, oh wait, oops, I totally got these backwards. Compulsory miss is if the address has not been asked for before, then it's compulsory. Otherwise, if we have asked for this before, go to step 2. My bad. So back to this. If this problem would not have been a miss had we had a better cache or a more associative cache, then you can call this a conflict miss. Otherwise, go to 3, and 3 is pretty easy. It's the capacity miss, which means, and what does this mean? It means we have asked for this address before, and even if we had a fully associative cache, this would still be a miss. And what does that imply? That really just implies that the only way to make this not a miss is to make the cache bigger. And that's what a capacity miss means. So that's kind of the step-by-step process you could go through to determine what type of miss you have.